Right, so here I will talk about all right. So I have covered this part last time, right? How to do encryption and how to do put the signature, and then you can do a secret communication between Alice and Bob. Right? And then there is actually RSA calculator. I was trying to do this with you, but if you can plug in the numbers right here, you can actually generate a whole procedure that I have explained to you. Okay. So I maybe it is called RSA calculator. So you might want to try it. Okay. And hash algorithm. Since you guys have the Python installed already, then you can do the hash, right, by yourself, and then make sure what you have learned in class stands. Okay, so let's how to put a signature. Okay, so this thing can be done by all right, maybe here, and how to put digital signature to a message inside your cryptography package. Right, you can download from Ethereum Foundation or from Bitcoin.org. Basically, there is an elliptic curve cryptography package, elliptic curve digital signature algorithm, and then you download that package. Then you will be able to put the signature on it, right? Or you can use this Bitcoin package, which does it for you. Right? There is a command line that how to put the signature on it. Okay, so Alice send Bob 2 Bitcoin, and then Alice should sign it. Okay, and then there is also a package called verify sign. Then basically that verifies if the sign is correctly done or not. Okay, against the published address. And then balance can be checked by looking at the address A. Transaction is complete if this is recorded into the block. Anonymity, Satoshi Nakamoto is using is A is an address of Bitcoin made from a public key of Alice. So if you create another public key pair, Alice has created another pair. Alice could have another address. Okay, so you could have many addresses, and then anonymity between the address and you can be created by having many different addresses. Right? So Satoshi actually recommends you have to use different address for each transaction in order to be in the safe place. Okay. If you have many transactions with the same addresses, then a hacker can try to hack the your address so that it can uncover the private key. So if you have many equations, you could create such an attack. Okay, This is like solving a simultaneous equation. If you have more equations with more transactions with the same address, then it will be hackable. Okay. And B is an address of Bitcoin made from a public key of Bob. That's about the transaction. Okay. So and then. In terms of doing the coding, basically it is already written, right? There is an API provided by this client software. Then it's just a matter of finding the right function. Okay? And now I'm going to talk about secure hash functions. Okay? And in this class we will use SHA-256 because Bitcoin and Ethereum uses this SHA-256. And then there is a SHA-512 as well. But, since it is twice longer, it is much more stronger than 256. All right, so CQ hash function definition is this. A hash function is a function, right? It maps something to a number space. What is that? Represented with the hash of input, then it will generate an output. And then this, which takes a text message, so input is text message or a single file. You put the file into it, it will generate 256-bit output. So we call it summary of this file. Okay, summary of this file. Okay, a text message as its input and gives as its output a fixed number of binary bits. So if it is a SHA-256, 256 bits, right? Or if it is 512, SHA-512, it will generate 512 bits, right? Ones and zeros, right? Of length 512. Okay. So this output is a number. Okay, output is a number, integer, right? Right. So what is a hash function? Bitcoin uses the hash CQ hash function 256, and the length of the output bit string is 256. That's what it means. And then the input to a hash function is a text message or a file. That's what I said. And then here input output relation. So message is this one. Let's suppose Bob, I love you, Alice, right? Bob, comma, comma, I love you, period, Alice, period. And then you put this into the hash function, it will generate this output. Okay? And then is this 256 bit? Probably yes. And how do you know? Basically, what do you think this one is, each number?
16 bits.
Eh?
16 bits.
16. Hexa. Hexa representation. So this one, 0, 1, 2, 3, and then all the way up to 9, and then that's 10 digits, and then you need 6 more. So A, B, C, D, E, F. So that's a hexa number. So hexadecimal. So if this is hexa, then the 256 divided by 4, that should be equal to 64 hexadecimal numbers. So this, if you count this will be 64 digits, right? Hexadecimal digits. All right, a string of 64 hexadecimals or a string of 256 bits. Okay. So what is 2 in binary digits? 0, 0, 0, 0, 0, 1, 0, 1, 0. 0, 0, 1, 0 is 2. Okay. How about F? Binary. 1, 1, 1, 1, right? Okay. All right, so that's this output. And conditions for good hash function, it should be one-way function because it has some purpose. So with a little change in the input, the output is completely different. That's how you make a one-way function. If it is not like that, for example, in an ordinary function, if it looks something like that, like this continuous one, right? Or some, close points like that. If a function is like that, and then this is the input, then this is the output, then if you change a little bit, then it will be the output near the first point, right? This type of function is not one-way function. So here we want a random output. For example, if you you don't want the input-output relation like that. We want the input-output relation. If you have x1, this is y1. You choose x2 near x1, then this is the output right here, or somewhere in this space. But we want the effect of random mapping, right? If you choose another one, maybe this is another number right here, but there is no relation between these 3 points. It just make you look like you are randomly picking this number, right? But here, random here does not mean that it is not a deterministic function. It is a deterministic function. If you choose the same input, let's say x1, put it into this function, right? Each time it will give you the same output y1, okay? But the relation of this mapping relation, that's look random. That's what I'm saying, okay? So input distance has no relation to output distance, okay? And collision free. Given y, hx, finding x1 not equal to x, such that hash of x1 equals y shall be almost impossible. What does this mean? That's what we are going to find out. Okay? So given y, hx, finding x1, another input, x1, which is not equal to x, but the same mapping, so h of x1 is equal to y, shall be almost impossible. So I have given a certain file, let's say, so in this notation, hx, okay? So, all right. I put some x, and then I get y. And then I want to find this mapping, right? That y is actually equal to, y1 is actually equal to y. I want to find this, but this event is very difficult to occur. That's what I mean, okay? So by the way, I'll just give you the definition of this statement, and then I will evaluate this statement in the following chart, okay? And then that's collision-free, what collision-free means. And then collision-free stronger means finding an input pair of different messages, x and x1, which leads to h of x is equal to h of x1 shall be almost impossible. So these two are very similar. Let's do the illustration. So illustration of one-wayness. x1 is this message. Now h of x1 gives you this number. And then I changed a little bit in example number 2. For example, I put the period here, but I didn't put the period here, right? So there is a slight change in the input. But as you can see, if you put the this message into the hash function, it will give you this number, which is completely different from this right here, okay? And ex3, now I have changed a little bit here as well. Can you notice where the change is? Huh? Loved that. I have added the D here, right? So a slight change as well. But the output is completely different from the previous ones. This one and this one. They are completely different, right? So this is what I mean by randomness. But I'm not saying that function is random, okay? If you put same input, then it will give you the same output all the time, right? But from here and there and here, it looks random, right? On the range space. the selection on the range space looks random. That's the effect that I want. All right, and a tiny difference in the input creates big difference. Note that there is a very small difference between x1 and x2, but the difference in the output is huge. Right? That's the effect that I'm saying. And then this creates one-wayness. One-wayness here means that given the output, you cannot determine what was the input. Okay? Unless the previous continuous function, given the output, you can determine the input, right? So it's invertible, but this one is not. This property can be utilized to spot out a tiny alteration made to an original input file, right? So if there is a little bit of change, the hash value is completely different. So if someone made any alteration to the record, then it will be revealed because you have different hash. A tiny unnoticeable alteration to human eyes, and thus is difficult to be detected by human eyes, but can be magnified into easily discernible hash difference. That's the purpose of a secure hash function. One purpose. All right. So input output of SHA-256, and then since you have Python library, you can find how to use SHA-256 function there, and then you will be able to do this experiment by yourself. Right? Right? Same thing. And then I loved you. And then this is the input-output relation. So I will designate X to be the all the possible inputs. Okay? And then designate Y, set Y to be the all the possible outputs. Okay? Input and output. So input set, output set. Okay? Then we can entertain the mapping relation from X to Y. Okay? All right, and here is the SHA-256 algorithm. You can find it in NIST, and then you can click here. And it looks like doing some additions and multiplications and modulo operations, so that if the output of the additions and multiplication grow outside of the range, what does it do? It wraps it back into the interval so that things are mixed up many times, so that it creates a random looking output. So that's what it is, but I'm not going to go too much details into the SHA-256. And then, but you can utilize it and then see the effect of using this algorithm. Okay. So here is what is actually going on. So there is a large set of input, because there are large number of possible files as an input. So it is a larger set than the output set. So in order to exaggerate that, I have here input set of 6 messages, 6 different messages, and then I call this SHA function, SHA-H. So it is input set size of 6 to SHA output of size set, which is 2. Okay, 6 to 2, and then it does the mapping, right? So John maps to 1, 1. John loves Nancy maps to 1, 1. Christmas maps to 1, 1. And then Mary maps to 0, 1. Mary loves John 0, 1, and so on. So when you take a look at this, should collision occur or not? Collision here means same output with 2 different inputs. That's what it is, right? Should occur or not? Because the size of the summary set is smaller than the size of the input set, collision must occur, right? But here, here is this tricky statement right here. Collision must occur, but it says you never encounter one. And basically that is this statement. One can hardly encounter one. We want to make this type of a situation for SHA algorithm. How can you create that? Basically, that is created by having large output set. 256 bit is large enough so that you can make this statement valid. Okay, you will see what we mean by that. Okay, so here is the input size set X. X is a message set. This message is up to 1 megabyte in size. Each of these file or message is a number in the number space. So how large this set is. So what is 1 megabyte? 1 megabyte is 1 million byte, right? What is 1 byte in bits? 8 bits. So this is like 8 million bits in the ballpark, right? I'm not byte megabyte here is 1024 or 1 kilobyte is 1024, but I'm just treating it as 1,000 byte, okay? Because I am interested in the order of magnitude because this is a huge number. The little bit of teeny weeny details doesn't matter. Doesn't make any difference. And then what is the size of the output set? So here input size set is this can be described by 8 million bits, right? Here output size is 256 bits. 8 million versus 256. Okay, that's the difference. So these black dots are 64 hexadecimal. Each of these balls, white balls, represent a file, okay, or a message up to 1 megabyte. Why I'm choosing 1 megabyte? Because that's the block size, maximum block size of a Bitcoin network. And then probably the same for the Ethereum. So, but please don't pay too much attention to the detail of exact, what is the exact block size and so on. But try to see the magnitude. Okay? Magnitude is important. Okay? Order of magnitude here is important. Okay? And here x, small x means you select one x in this set, put it into the hash function, you get y, which is the element of this set. Okay? Since this set is smaller than this set, there must be collision, right? But you never encounter any collision in your lifetime. We want to entertain that statement. Okay? So here, cardinality of the input file set. Bitcoin is 1 megabyte. That's why I'm using this number, 1 megabyte. What is the cardinality of the set of all possible input file sets? That's what it is. So there are this many different files, 2 to the power of 8 million files. So that is the cardinality of the input set. If you translate this to the decimal number, that is 10 to the power of 2.4 million. So this is huge, right? 2 million zeros, right? 10 times 2 million zeros. So this is a huge number. What about the output? 256. And then what is the cardinality of the output set? 2 to the power of 256, which is in decimal 10 to the power of 77. Okay? So for each y in set y, how many input files x in X there such that you have this. So what I'm asking here is how many different X's that are possible to create the same hash. That's the message that I'm getting here, right? So then I need to talk about the pre-image. Okay, so here you have the input files that creates same hash y1. There are another set of input files that creates same hash y2. Because there are 2 to the power of 8 million, right? This type of mapping should occur, right? Because this input set is so huge, right? This size compared to the size in the output. All right. Then size of input set per hash output. What is the average size? I'm asking you the average size of the input file set whose element leads to the same hash output. Let's just take the average, okay? Then on the average sense, how large is the pre-image set for same hash? Okay? How large is it? Without seeing the next page. Can you make a guess? Anyone? So here I have an input set. I have an output set which is tiny, right? There is 10 to the power of 77 elements right here. In the input, how many elements? 10 to the 2.4 million. This many elements right here. So I am finding out the pre-image of this output. How many elements on the average do I have here? That is what I'm saying. Right? So basically, I'm dividing the whole set of X, dividing the whole set of X by the number of each output, which is 10 to the power of 77. So that is what? 10 to the power of 2.4 million divided by 10 to the power of 77. So that is, this is just like, this is just almost the same, like and minus 77, but compared to 2.4 million, 77 is almost nothing, right? So there are a lot. So each one of these elements maps to that output, right? Each one of these elements. Okay. If you choose another set pre-image, then any one of this many elements maps to this, maps to that same output, right? That's what this picture is telling you. All right. So there are a large number of collisions possible, but here what we are entertaining right now. But you never occur. You never encounter such an event, right? So for example, what is the collision event? So for this output, let's call it Y1. H of, let's call this X1, this X2. H of X1 is equal to Y1. And then this one, H of X2 is also equal to Y1. Then there is a collision. All right, so that's what I'm doing right here. And then that's the order of magnitude, right? Because I have taken the log, right? So 10 to the power of this many. And then collisions are bound, but can you find one? Right? So then that is this statement, right? Collision must occur, even abundantly. Consider any two different files, x1 and x2, such that there is a collision. Okay? But this event is very rarely occur. That's what this one says. for any file x3 in x, but not in x, y, we note h of x3 is not equal to y. What do you mean by collision free then? Okay. So in order to see this, we want to consider a small problem. So in a small problem, we can see what's going on much better. Okay. So suppose that input x is a file of a size up to 1 kilobyte only, 1 kilobyte. Okay. And then SHA output is truncated to 10 bits only, 10 bits. And then Bob has found that the input file x0 has the hash value y0. What is the input file set? 2 to the power of what? This 1 kilobyte. So 8,000. 2 to the power of 8,000. What is the size of the output file set? 2 to the power of 10. So it is the only 2 to the power of 10 is 1024, right? So it's about 1000, right? So Bob selects a file x1 at random from his desktop computer, size smaller than 1 kilobyte, and runs it through the truncated SHA, which is the 10-bit. And then what is the probability that this output is the same as the first output, y0? Okay? So basically, that is the same situation right here. Then the 2 to the power of 8,000 divided by 2 to the power of 10, right? In such a case, it is, this is a decimal number. So 2.4, so 2,400 it is. And then S of y is 3. So in terms of power exponent, it is 2,400 minus 3, so it is about this much. So the set size is 10 to the power of 2397. Okay. And then now I want to calculate the probability, right, of selecting different output, but land in the same hash output. Okay. So input, they are different, but the same output. So what is such probability? That probability is calculating this event, right? And then, so in this case, H is 0 has been selected already. So H is 0, let's call it right here. So I'm doing a smaller problem. So 10 to the power of, 2 to the power of 10, so it is about this order, right? So I select 1 here, and then I get y0, right? And then what is the probability? What is the probability of collision, right? So how do you calculate this probability? So you get this output, that means pre-image set is this one, right? And then what is the size of this set? You divide this 10 minus 3. So that is the number of elements in this set, right? Okay. So what is the probability of collision? If you select any one input from this set, there will be a collision, right? Two different input, same output. That's a collision, right? So what is the probability of selecting a member, an element in this set which excludes the first one and then leading to the collision? So that is, you are selecting this out of this many members. What is the probability of selecting one member within the set? So that's the total set. right? And then what is the size of this set, isn't it? So that is
2397.
huh?
10 to the power 2397.
2000.
2397. 2400 minus 3.
Yeah. That's good. Okay, thank you very much. So without doing that arithmetic, it is this, right? So that is what is going on here. So why did I extract 1 here?
One value is already chosen.
Yeah, one value that was already chosen, which is leading to y0. I have to exclude that from the denominator and the numerator. But since these numbers are big, it doesn't matter much at this point. Yeah, so here is 1 over size of the pre-image set. No, so size of the output set, sorry. Why is the output? Okay. So that is actually, this, event, right? So this is number of outputs here is dividing determine the number of different mutually exclusive sets, pre-image sets. So basically, that's it. So 1 over the cardinality of the output set. In this case, it is 1024, right? Because we are doing a smaller problem, 10-bit, okay? And then now I am progressing to 2 previous outputs. X0, X1 has been selected, but there has been no collision, right? So no collision. So I have doing what? I am determining 2 different pre-image sets, right? And then selecting the third one. Then what is the probability that this third one belongs to either that one or the other set? So all I have to do is 2. Okay? 2 divided by the output size set. And so